So we're first going to talk about ordinal utility. And with ordinal utility, I mean, the absolute numbers don't matter, it's just the ranking. So absolute numbers do not matter. Just the ranking. Of the bundles, in case that isn't clear. So in the same vein, the size of utility difference between, so BTW for between bundles doesn't matter. So it's just which has a bigger number. It's not how big that number is. It's not the size of the difference in utility or utils between two bundles. It's just about which one gets more. So it's just a ranking. So because of this, we can talk about monotonic transformations. So we kind of talked about monotonicity before, and we talked about preferences, right, and indifference curves. So since only the ranking matters, as soon as we find one way of representing these preferences with the utility function, we found like an infinite number of ways to do so. There is no unique way to assign utils. So just utils are just like the amount of utility. Utils to consumption bundles. So if we find one way, we find an infinite number of ways. So positive, because we're going to mostly be working with positive, monotonic function. So what that does is it transforms a set of numbers. Maybe I'll underline it. So it transforms a set of numbers into another set of numbers that maintains or preserves the order. So for instance, you have this, function f of u. This f is some monotonic function. And basically it's a monotonic function if we have two amounts, u1 and u2. And when we apply this function to these u1 and u2, the order is preserved. So if u1 is greater than u2, then taking a monotonic, applying a monotonic function or making a monotonic transformation of u1 and u2 is going to maintain the order. F of u1 is still greater than f of u2, just like u1 was greater than u2. All right, so I'm going to erase this and we'll write a couple examples. Maybe it's a little bit out there right now mathematically for you. We're going to write down a couple examples. It's just like cubing a number and multiplying it by 2 or multiplying it with some positive number, etc., etc. So in case that's a little bit confusing, some examples of monotonic function in terms of like that f function that we were just saying. So, you can multiply it by 2. That could be the function you use, or any kind of positive number. We can add a number we could raise to the power of 3, or of an odd number. And these are all monotonic or positive monotonic transformations or monotonic functions. And so if we want to think about what the change of this monotonic, or the change of this function is from a change in u, we could just do f, this function at u2 minus this function at u1 over u2 minus u1, and that's going to be how this function f changes when we change u a little bit. And so notice that the numerator and denominator will have the same sign. And so if you want to kind of visualize these monotonic functions, you can do one monotonic and one not. So let's put this function v up here, and u down here, and u and v, where v is going to be like f of u, basically. So if it's monotonic, it always has a positive slope. So it has a positive rate of change. Positive rate of change. Where this is like v equals f of u. If something's not monotonic, it could go like up or down. So it's not a positive rate of change for all u's. It could go down, for instance. So with going from here to here, this v, which is f of u, is going to go down as u goes up, right? So this is not monotonic. And so we're thinking about, we can do any monotonic transformation and that's going to keep the order of these, this set of numbers the same. And we can start to think about that relating to that utility. Remember, we want to maintain this order of bundles. Well, any monotonic transformation is going to maintain that order. So building on kind of what I was just saying, if f of u, so to speak, is a monotonic transformation, of a utility function so remember, a utility function is kind of just like u of whatever, like x1, x2, for instance, if we have two goods, that represents some particular preferences. Then applying this transformation to u also represents those same preferences. Then f of u, let's say x1, x2, for instance, also represents those preferences. And so kind of let's go through the logic why. Hopefully this is, we're just going to kind of go in 3 steps and kind of like think our way through why this is true, I guess. So we have some utility function, u, the amount of good 1, the amount of good 2. So we're applying some function to the amount of each of these two goods, and it's giving us a number, right? And we're saying this represents some preferences. in that u x1, x2 is greater than u y1, y2, if and only if this bundle of x1, x2 is kind of strictly preferred to this bundle y1, y2. So understanding this, we're assuming this utility function u of x1, x2 represents these preferences. And we're going to talk about how to come up with these utility functions afterwards, or kind of just the classic ones we're going to end up seeing in this course. So we're starting there. We're assuming this utility function represents these preferences. And then if f of u is a monotonic transformation, then ux1, x2 is greater than uy1, y2, if and only if applying this monotonic transformation to each of these bundles, you're going to have the same relationship. So x1, x2, oops, if and only if, I think I'm going to need a new line here, f of ux1, x2 is greater than f of uy1, y2. One more bracket. So we're basically doing this monotonic transformation, and that means if this utility of x1, x2 is greater than the utility of y1, y2, then applying this monotonic transformation, that's also going to be true. Well, the only thing that matters is like the order and not the absolute number. Then this, transformation of this utility function represents the exact same preferences that we had before, because it's only the order that matters, and this monotonic transformation preserves that order. Well, this means that f of u x1, x2 is greater than f of u y1, y2, if and only if this bundle x is strictly preferred to this bundle y. So it's going to represent the same preferences. Since again, it's only the order that matters and not the absolute amount. So you can apply this monotonic transformation to any utility function, and it's going to represent the same preferences. So essentially, these utility functions are just a way to label these indifference curves. So I don't think I have enough room to write this, so I'm going to erase this and let's kind of sum up what we kind of just looked at, or what we kind of just discussed. So let's kind of just sum up what we looked at with ordinal utility. So utility functions are essentially just a way to label indifference curves. So it's basically a way of assigning numbers. Oops, numbers. Sorry about that terrible M. To different indifference curves. To different indifference curves. Where the higher number means higher utility, or more preferred. So higher indifference curves, higher numbers, for higher indifference curves. But all we're doing is labeling them, but the absolute number of those labels doesn't matter, just the order, just the fact that one number is bigger than the next. So a monotonic transformation is just coming up with a slightly different way of labeling them. But again, the absolute number doesn't matter. So instead of like 1, 2, 3, maybe it's like 1, 6, 9, or something like that. Or 1, 4, 9 if we were like squaring it or something like that. So all they're doing is just like relabeling it. So this is what ordinal utility is all about. So ordinal, think about order. Like order is the only thing that matters. The next kind of concept of utility we're going to look at is kind of cardinal activity, where the absolute numbers and the differences matter. You know, it's going to turn out that we're going to use this ordinal utility, but we should talk about cardinal activity as well, or sorry, cardinal utility as well.